So Kevin is presenting Knock Knock Log, Threat Analysis, Detection and Mitigation of Covert Channels in Syslog using port scans as cover. So this paper was written by Kevin Lamshöft, Tom Newbert, Jonas Heilscher, Klaus Wielhauer and Jana Dietmann. So I'll hand over to you now, Kevin.
Thank you very much. All right, so thank you for the nice introduction. I'm Kevin Lamshöft, and I'm from the Otto von Guericke University. This is basically a joint work together with the Brandenburg University, so I'm more like the offensive side, and the guys from the Brandenburg University are more from the defensive side. And Jonas Hirscher, actually, he was working with me at the Otto von Guericke University, but now he's doing his PhD in Bochum, so we unfortunately lost him, but I hope he's listening. It was a very nice work, and yeah, I'm a PhD student too, and I'm very happy to kind of talk today about a little bit on covert channels. So information hiding, especially in research, gained a lot of traction in the last years, especially in network covered channels, and we especially see this as well in newer malware generations. So, for example, here we have Daxin BVP47, which is by the Equation Group, which is associated with the NSA. Lazarus is like advanced persistent threats, and Tiny Turler, for example, is a small backdoor by the Turler Group, which was apparently used in the retrieval of the Western states in Afghanistan. So it's really geopolitical and in parts very targeted attacks, and the aim basically is to be stealthy, be as long as possible undetected in the networks, and do exfiltration or infiltration. So this is the one hand, and on the other hand, Syslog is one of the go-to standards basically for logging system events, and it's also a network protocol. And I will talk today about why it is so interesting for covered channels. And then there's another trend we see, which is basically trying to hide in seemingly harmless attacks. And there was, for example, an incident in an Indian nuclear power plant where they thought, all right, this is a malware, which is just a crypto miner. Well, actually, it was a really targeted attack on gaining insights and exfiltrating sensible information. Basically, we took both Syslog, and then we thought, all right, we stumbled upon basically that we can use port scans to trigger Syslogs and hide within these port scans. So why is Syslog so interesting from our perspective as information hider? So as I said, alongside SNMP, actually, it's one of the go-to standards for logging system events. And not only that, it's also a network protocol, so the logs, so if you have multiple hosts, for example, the logs are often generated, aggregated, and sent to central servers. So they're going over the network, and this is normal Ethernet, IP, TCP, UDP stuff. And usually it's unencrypted. There's some ways to encrypt it though, but it's mainly unencrypted. And therefore you can do some basic network cover channel stuff like hiding in header fields, in payload fields, modifying stuff. And the other thing is logs are actually basically plain text, right? So you can do interesting things with text stenography, which is like capitalization of letters, uppercase, lowercase, stuff like that. And the other interesting thing is that logs are basically there to log events, right? So from a standpoint view of an information hider, basically you can trigger events in such systems basically to produce logs that you want. And for example, by if you have a certain event that is logged to a specific point in time, for example, this could encode messages. And the other thing that makes it very interesting is Syslog can be retrieved at several locations. I will talk about that soon, and also in different points of time. So basically we have a locational and a temporal aspect. And the temporal aspect is kind of the persistence. So the interesting thing is that on the host, for example, we heard this today actually. There was a question that we have so many data. So if you log everything, right, you have many data. And basically, therefore, you have log rotations. And this is, it depends. It can range from hours to days to weeks. It of course depends on how much or how verbosity you have in the logs. And then if you aggregate those logs on central servers, then they might last for months or even to years, or in factories, for example, on nuclear power plants, it's lifetime basically of the factory, for example. And the other thing is, in network traffic, so if you don't record the network traffic, of course, then if you embed something into syslogs, then they're basically gone when the network packet is not captured. And the other aspect that's coming with this is the locational aspect. So you can, if you embed something into the syslogs, you can retrieve actually this hidden information at different locations, like on the host systems, on the servers, in the network traffic. And as we heard in the keynote today, of course, you have nowadays systems like security information and event management systems like SIEMs, where also logs are sent to. So this makes it very interesting. And this leads me to our basic threat scenario we used in this paper at least. And this is actually based kind of on the tiny Turler backdoor, which is really just a little backdoor to keep the door open and maybe load some further malware components. And here on top we have Alice, which is the adversary running a server in the internet basically, and we have basically standard cyber kill chain. We have some malware infection using spear phishing, water holing, whatever you like basically. And have an exploitation. Then we, of course, in many cases, we have lateral movement, especially in those advanced persistent threats. They infect generally multiple systems and even use them as a proxy. And basically, the idea here was, so Tiny Turler, for example, would here now start doing a reverse channel to Alice, like just an HTTPS call every 5 seconds and asking, hey, is there anything I should do? But this is actually more likely to be found, of course, and we wanted to infiltrate information into this network and basically do this in a very stealthy way. And we came across port scans, for example, using Nmap, and it's like the idea is that Alice is performing port scans, which is like knocking on the firewall, seeing which ports are open, and and the idea is basically to hide within the sequence of the ports that are locked. But I will show you this in the next slides. And the basic idea is that the firewalls lock these port locks. So we have the locks on the firewall, and then they're basically aggregated on syslog servers and even the SIEM systems, from where Bob, which is then the actual infected system, compromised system in the network, would retrieve the logs from the server. So this is the basic threat scenario. We extended this a little bit and also included a kind of reverse channel. So now we have a full command and control channel. This can basically, so here it's a DNS cover channel, but it can be basically anything. So there's so many right now published. For example, we also have a NTP cover channel and other time synchronization techniques or cover channel techniques to exfiltrate information. What makes this very interesting here is that it's quite common in covered channels to use symmetric encryption using shared secrets. But in this work we wanted to do it a bit different. So we use fully asymmetric encryption and key derivation functions basically to derive. It's called a stego key, which is then used to drive the embedding algorithm. So basically how you hide and where you hide specifically in the port scans. But I will show you that in the next slide. And we also stumbled upon another Covert channel, which is actually pretty nice. We figured out that you can store your public keys on GitHub. So if you have a user account, you can store your keys at github.com/your-username.keys. And yeah, this is pretty nice because if you want to do key exchanges, for example, you can do this quite in a stealthy way because you only need an HTTPS call to github.com that's very inconspicuous in many networks. And yeah, this is actually a pretty nice one. Nothing too fancy though, but it's quite nice. And yeah, this is how the embedding then works. So if we have Alice and yeah, she's having a hidden message she wants to send to Bob. So this can be malware components, for example. So other parts of the malware, and then it's encrypted using the asymmetric keys, of course, and then we get the cipher. And the encryption is actually quite important to us because it increases, of course, the entropy. So we have a high entropy bit stream, which we use to encode the message. So we use a pretty basic encoding here. So we really just use an odd-even scheme here in the port numbers. So basically a even port number would encode a 0 and an odd one a 1. So that's pretty easy. But the funny thing is actually that we, from the key exchange, we derive with the key derivation function, we derive this stego key, and from that we derive a seed. And the seed then is used on both sides to run, to seed a pseudo-random number generator. And basically with that we select, so for example in Nmap scans the first 1024 ports, and but the first 21 or 24 are always the same, and the rest basically is selected fully random. So this is why it's so interesting to embed there, because it's a random sequence. And therefore the detection, of course, is quite difficult. And what we do here is we do not use the whole sequence, we use a subset. So this can be a dynamic, basically we can achieve a dynamic bandwidth, a dynamic steganographic bandwidth. So this is basically the main part, and this makes stag analysis, of course, very difficult because when you try to attack this Covert channel, you don't know actually where the covered message is in the port scan. So even if you know there's a hidden information in the port scan, it's very hard to find it. And then, of course, the port scan is performed against a firewall, and then this results in the logs. And the logs are then distributed on the network, and the malware would now try to retrieve this. So there are several options. Basically, you can do man-in-the-middle kind of stuff. You can compromise the Syslog servers. So there's many scenarios. And as I said, so basically, if you would do it with Nmap, you come up with 1,000, basically 1 kilobit, so 1,000 bits, and you can, of course, increase it by using subcarriers. So those are TCP port scans. And so you can use common TCP Covert channels as well. So we took a look at several published Covert channels and had a look if they would work in open source firewalls. And some would work, some would not. But this would help at least increase bandwidth. But this also, of course, is then easier to detect. So it's always, it's always like a cat and mouse game as well. So of course we have some indicators of compromise. So the first stage, so the common compromise of the system, of course, would, alongside the kill chain, would result in several IOCs. So this is basically like the normal malware stuff. So the interesting thing is then what IOCs do we have in the Covert channels? And yes, it's not so much, of course, the port scans, but yeah, port scans are quite common, so it's not that conspicuous, and but the retrieval, of course, would result in some artifacts which might be detectable. Yeah, so my colleague then Tom's task was basically to detect this Covert channel directly in the port scans. And yeah, we're doing this usually with handcrafted features and yeah, classic machine learning basically, but this was not working properly. And so he basically came up with the idea, okay, how maybe we can use deep convolutional neural networks. And yeah, he came up with an approach using inception and transfer learning. And yeah, the challenge was basically, yeah, DCNNs are mostly used for images, right? So how can we represent the port scan as an image? And yeah, he came up with a good idea. So basically, it's really just the port number is then used as a pixel. And yeah, he came up with 10-bit basically pixel because it's 1,000 port numbers, and this results in a gray value image. And yeah, this is a 16-bit PNG file. You have to rescale it a bit to use the DCNN. And yeah, then he tried to find basically patterns in this noise patterns to see if the embedding algorithm, which is inserting the hidden information, would result in certain patterns. And yeah, on the training data, the accuracy was, so we did several training sets with different bandwidths. So we have basically no steganography in it, then 256-bit, 512, and 768. And yeah, on the training data, it was looking very good. But yeah, on the test data, I'll get to this actually. So here, this is the test data, and this is the training data. So on the test data, we see that on low bandwidth, basically, it was not very good. And but we see at least an increase in when we increase the bandwidth as well. So this is kind of a general concept which we see, which is called steganographic cost. So basically, if you alter the carrier, basically you make detection more easier. So here's, of course, still ways to improve. So what can we do else? So of course, one way would to modify the logging behavior. So basically not log not every single port, but aggregate it. So basically just log that there's a port scan basically done from ports numbers 1 to 1000 or something like that. And yeah, the thing is with covered channels in general, or information hiding, is basically to reduce redundancy in the networks, cut down entropy where it's possible. Yeah, basically use, for example, only lowercase, so you can do traffic normalization, and yeah, basically have better ways to detect modifications to those things. And if you do these event-based things like triggering these events, so basically you can also do event-based anomaly detection in such networks. So yeah, to sum it up, Syslog I think is very interesting for covered channels and has many opportunities for hiding information in it. Such event-triggered covered channels are actually quite interesting, and I think there will be more in the future. And yeah, hiding and harmless looking attacks is really a thing, so keep that in mind, especially you incident responders. Yeah, and I really recommend active measures like traffic normalizers to make this detection actually more easy. And of course, yeah, we tried novel approaches, and we will see if this will be continued in the future. So yeah, thank you very much for listening.
Thank you very much, Kevin. Have we any questions? Yes.
I wondered if, so it's very difficult to detect this kind of exfiltration on the log files themselves. Did you check how good it is to see the access to the log file that's now more frequent, if it is easy to detect?
Yeah, this is definitely a way to detect such channels. So because you have, the malware has to retrieve it somehow. But the problem is that often those Syslog servers are just common Linux servers, and are often compromised with the same malware that is used before, basically. So before the lateral movement, but yes, definitely, unusual access to logs is definitely an indicator of compromise, I think.
Okay, have we any other questions? Kevin, in terms of the firewall to log the events, how is that configured in terms of port accessibility?
Yeah, this makes really a difference, of course, which ports are blocked or not. So basically what you have to do, so in our lab we just had them in a default state and default logging behavior. But basically what you would do is to do prior reconnaissance, basically to see which ports are open so that you can filter them out.
Okay.
Yeah, that's absolutely true. It's a bit of a limitation in that.
Okay, thank you very much, Kevin. Yes, Ed.
I was thinking about this really interesting problem about detection based on looking at the ports that are being used. And I was wondering if any kind of, you considered using any sort of frequency analysis approaches to determining whether what you're looking at is a random distribution versus one that's actually encoding data. Also, are there any heuristics you could potentially pick up on, such as, Nmap not repeating scans of the same port, but perhaps an encoding of information might do that?
Yeah, very interesting. So the thing is, we actually used Nmap and modified the source code. So we have basically built an API so you can basically give him a list of ports it should use, because in default it's really using random values from the operating system. And yes, so basically, but this would be a way, maybe, yeah.
Interesting. Thank you.
Okay, any other questions? Okay, thank you very much, Kevin.
Thank you.